So we've got atomic operations in C++. These are sequentially consistent by default. And what that means is if you declare an atomic object and you load it or store it to it, you get full interleaving semantics across all the atomic objects you have. And but that's only if the default is used. This is expensive, and this is especially the case on weakly ordered architectures. In many cases, you don't need this interleaving semantic. And this is allowed. You can avoid that by using memory order enum values, particularly memory order relaxed, which is what we're dealing with today. And memory order relaxed is wonderful from a number of viewpoints. I mean, if you give a memory order relaxed load, you get a load instruction. And if you do a memory order relaxed store, you get a store instruction. This is just wonderful. You have control, you have great efficiency and scalability, assuming, of course, that your objects are of such a size that the hardware can accommodate this, just a load, just a store semantic. Unfortunately, there are some complications. You see, we don't just have hardware to deal with, we got these things called compilers. And the compilers introduce some interesting things out of thin air and read from untaken-branch. Now, Hans will be describing these in more detail in later slides. I'm just going to give a quick overview of a history of the problem right here. Small is somewhat sarcastic. With OOTA, you can get arbitrary behavior almost in many cases, in theory. And Java has a similar problem that they've been attacking for more than 20 years without really getting a solution. Nevertheless, in the last few years, we have had some progress. First off, we now have ways of classifying what the heck OOTA is versus just simple reordering. Before these two advances, we didn't even have any kind of agreed on definition of exactly what OOTA was and wasn't, aside from a set of litmus tests on both sides. Unfortunately, the first thing was a paper that a bunch of guys, myself, did, a C++ working paper we did some years back. It's not even an algorithm, it's a decision procedure. You have to have a human being and with a human being execute it. You have to have personarial creativity to get the right answer. More lately, there have been some academic groups that produce some very good, there actually are algorithms, but they aren't things you can put in a compiler, at least not yet. So personally, I expect that we will get to something we can put in a compiler sooner rather than later, but if you look at the history, we've got probably a few years, maybe even 5 of them, before we get the statement of a solution. Then we've got another couple of years getting the standard, another few years to get it propagating through the compilers. So we have to deal with for some time. Now, we do have one pragmatic solution that Hans came up with, among other people, and they seem to have a formal variant. But what happens there is you get otherwise unnecessary overhead on weakly ordered algorithms such as ARM. Now, Hans did provide a refined proposal that adds a memory order load store, memory order enum, that avoids it where you don't, so you can still use memory order relaxed where you need it. But in any case, we've got a problem. And at this point, what I'm going to do is go to the next slide and let Hans take over and tell you exactly what OOTA and RFUB is. Go ahead.
Yeah, I'll go ahead and describe what the out of thin air problem is. It's easiest to describe this by contrasting a bunch of different kinds of examples. So I'll start with an example with the questionable outcome, in fact, is intended to be allowed and we must allow it. Then I'll describe some out of thin air examples where we really don't expect the questionable outcomes described in those slides to occur, but we don't really know how to prevent that by phrasing the specification correctly. And finally, I'll look at a more modern variant of this that's sort of in between the two and points out exactly why this is difficult and why we might have trouble distinguishing between those two. So let's go on. The actual C++ syntax in this area was designed on the assumption that memory order relaxed atomics are very rare and should be highlighted, so it has a rather verbose syntax. Unfortunately, that doesn't play well with slideware like this that tries to look at different litmus tests. So we'll introduce some shorthand notation here, which isn't quite C++. In general, when we use variables like x and y, those will denote potentially shared memory locations, global variables or the like. R1 and R2 will denote locals You can think of those as being registers essentially, but they're in C++ terminology, they're address not taken local variables. We'll generally assume, unless we state otherwise, that all shared locations are initialized to 0, null, or false implicitly. Sometimes we'll make that explicit. And we'll abbreviate the actual C++ syntax appreciably. So rather than saying load of memory order relaxed, we'll usually put a relaxed suffix somewhere in the vicinity to indicate that the memory operation that's involved in that statement is intended to be relaxed. And you're intended to fill in the full syntax here using the std : memory order relaxed. Okay, next one. So this is the basic example that actually has to be allowed. So what we have here is a simple program operating on 2 atomics and 2 threads. Thread 1 basically copies x to y by loading x into R1 and then storing the result back into y. And thread 2 loads y, but then they just store 42 to x. Both x and y are initially 0, and we would expect that if this were just executed with sequentially consistent semantics, then in fact both R1 and R2 should be 0. Or at least one of R1 and R2 should be 0, since in particular R2 should be 0. However, can we have the next slide? Actually, sorry, one back. However, in reality, we have to expect the case here where R1 and R2 are both 42, because we said that these were relaxed operations. So it's entirely acceptable for the compiler to reorder these and to initially store 42 into X in thread 2 and then load Y from R2. And if thread 1 just executes in between the store 42 into X and the load from Y, then we have precisely we have an outcome in which R1 equals R2 equals 42. And that's entirely reasonable and expected. Can we go on to the next slide? No, thanks. On the other hand, here we have a slightly different example with 42 is not explicitly stored and there are only zeros involved in the program. But if we see the same pattern of reads as in the last slide, where each thread sees initially in its load, sees the store of the other thread, even though it happens later, we can get a very weird outcome. So the outcome that we're concerned about here, and this is the canonical example for an out-of-thin-air execution, is one in which the value of 42 here doesn't appear in the program, but we suddenly get some value like 42 appearing in the output. So in this particular case, we have a situation where Y reads, where Y appears to be 42, then thread 2 stores that to X, then thread 1 reads the 42 that's stored by thread 2, and thread 1 again stores the value of 42 back. Let's go on to the next slide here to discuss exactly how this kind of thing might happen. So the kind of execution we're talking about here is one in which, say, the hardware or the compiler guesses somehow that X and Y are initially 42. So when we initially read R1 and R2 in thread 1 and 2, they both guess the value is 42. They then store 42 back to the other variable. And since we guessed initially that X and Y were 42, the compiled code now has to verify that that guess actually was correct and undo this if it was not. So at the end, we just checked that, in fact, the loads were okay and X and Y were, in fact, 42. But since we just stored 42 into X and Y, we can confirm that our speculation is correct, and we're now okay. This corresponds, again, formally in the C++ memory model, this corresponds to the case where each load sees the store that's produced by the other thread, the concurrent racing store produced by the other thread. And normally, well, aside from some things we'll talk about here, this is very hard to prohibit, and it's not usually prohibited directly by the formal aspects of the C++ memory model. Next slide. There's another variant of such out of thin air results that's even more disconcerting, really. And that's the following one. That's the one in which the stalls are not actually even present in the program. But what happens instead is we speculatively read some value at the beginning of the thread using a relaxed memory operation. And we speculate some value which is in fact not valid. So what happens as a result is the next statement generates, in the words of the standard, undefined behavior. But that undefined behavior can include storing something to the other atomic variable, which is being read by the other thread. So in thread 1 here, when we see a sub R1 is equal to 42, if R1 happens to be exactly the right bogus value, we may actually end up storing back to Y. So as a result of that, with this kind of behavior, we can again get R1 equals R2 equals 42, even though that's completely nonsensical, since we're reading from X and Y, which should have nothing to do with A and B. But formally, this has to do with the way undefined behavior works. And it also has to do with the fact that, again, we have this funny kind of pattern where with a load in each thread sees the concurrent store from the other thread, only in this case, the concurrent store isn't actually there. It's part of the undefined behavior. Can we go on? And this is sort of a more detailed example here of exactly how this would work. I already discussed this in the last slide. Again, it's the out of bounds accesses here that write to the other atomic variable. Can we go to the next slide? Outlawing out of thin air here is, as Paul already said, is actually a very long-standing problem. It's very difficult to define this in the specification. Until recently, we thought this was really purely sort of a specification problem, and in some sense, we just needed the right words. It's actually a little more than that, as we'll go into here. As Paul mentioned, Java, C, and C11 and C++11 tried and failed. Is the way it turns out, C11 and C++11 actually sort of had an attempted solution to this, which ended up being even worse than the problem. And this is a problem that continues to be investigated by many people here, including the WG21 concurrency group. Next slide. So what we actually have, since we fixed the bogus attempt to address this issue in C++11, is we have some wording in the standard which is embarrassingly hand-wavy and which nobody actually believed was sufficient even when we put it in the standard. It just recognized the problem, essentially. It just says implementations should ensure that no out-of-thin-air values are computed that circularly depend on their own computation. We knew from the beginning that this was really way too imprecise, but we left it in, embarrassment and all, anyway, because we didn't know of a better solution. Since this is sort of a hand-wavy restriction in the current version here, actually, let me try to, I'm being told that there's an echo here. Let me just quickly see if I can figure out the source of this. Unfortunately not. Okay, let me just continue here. So in order to deal with the presence of this this vague specification, we'll actually, for the purposes of this talk, introduce the notion of strict C++20, which is just defined to be, which will define to be C++20 without this hand-waving statement. So when we talk about whether something is correct in strict C++20, we mean that it's actually strictly correct by the precise part of the C++20 standard. We'll discuss that in some cases that's actually more restrictive than we need to be, perhaps. On the other hand, it's what we can define precisely, and it's what we can reason about precisely. Can we go on to the next slide? So I promise you another kind of example, which I'll only outline here briefly because going through this is fairly complicated and lengthy. That illustrates that that in fact this is more than a purely specification problem, in that there are in fact cases that are sort of in the middle where it's unclear what's out of thin air, what's an out of thin air result and what's not. So the example here that I have on this slide is very similar to this canonical out of thin air example, in which one thread copies X to Y and the other one copies Y to X. So what I did here is you see that code in blue here, in fact, and what I did is I added the code in green, which augments that a little bit. So I assigned 42 here. You can think of a local, it's not touched by anything else. I introduced that variable, and then I introduced some other code in green here, which in the interesting execution here, I can show is not executed. So it shouldn't actually matter, and it shouldn't affect the semantics of the program at all, since we know it doesn't actually execute. But nonetheless, with this additional unexecuted code in there, in fact, I can get the out of thin air result, and I can get it in existing implementations, in fact. So as you can see here, what I do is I just check if I don't see R2 equal to 42, and then I assign R2 equals 42 afterwards, and I keep track of the fact that I took this branch in the if, and then assign it back. And it turns out this has the effect of convincing the compiler that R2 is always going to be 42, which convinces the compiler that it's okay to reorder this again. But if that happens, I can get this execution in which X equals Y and R1 and XY and R1 and R2 are all 42, but assign 42 is false. So the only code I changed here was code that didn't execute. And the details for this example you can find in that code. Let's go on. Back to you, Paul.
This time, skillfully unmuting myself for a change. So this is a repeat of my last slide. We've got the history. And based on what Hans has told you, an excellent question is, in the meantime, before we get all this defined, before we figure out formally what out of thin air and RFUB are, where can you use memory order relax safely? And what we're saying, and this is the point of the paper and this presentation, in the meantime, you use known good patterns, okay? In other words, if you go off and randomly generate code that uses memory order relaxed, I'm sorry, but for the moment, you'll probably get what you deserve. Maybe OOTA, maybe RFUB, unlikely OOTA. There aren't many implementations that do that as far as we know. And the fact is that this is true of the other memory order values, but it's just that there are fewer counterintuitive pitfalls with those with acquire, release, and sequential consistency and so on. So again, if you're going to use memory order relaxed, you should use it in the context of known good patterns. And the link is to the working paper that Hans and I presented on this topic last February. Okay, so one question is, when is it fully safe? And here we mean fully safe within strict C++20 that Hans defined, where we exclude the weasel worded exclusion. And the advantage of staying within this bounds is that, as Tom said, we can reason precisely about it. And we know that adding unexecuted code isn't going to cause us these funny reads from untaken branches. And we're going to present some things, Hans and I will, through the rest of this presentation. Some of them are going to be fully safe. Others, which are important, are safe and are used heavily, still require the weasel words. And we'll distinguish between those for you. Okay, so let's look at some simple use cases first. One example is atomic counters, and these you update while you're running, and these might be atomic increments, relaxed atomic increments of counting events or something like that. Perhaps they're per thread variables, local storage, thread local storage, that is incremented only by the thread that uses it. And you only have these things happening in each counter. Nobody's looking at anybody else's counters until we get to the end of the program. All threads but the main thread have terminated, and now we're going to read them out and print them. In this case, we don't have racing stores, and we can't get the canonical OOTA pattern. So this use case is safe, even in strict C++ without the funny advice. Another category is where the ordering is provided by atomic thread fence. All right. So rather than say memory order release store and then a memory order acquire load or whichever, we have an atomic thread fence of acquire or atomic thread fence of release in the proper places. And in that case, those atomic thread fence calls prevent the canonical OOTA pattern from forming. And finally, this one may sound kind of useless, but it's used surprisingly often, and that's where there is only one shared object. For example, we might have some independent algorithms running within a given multi-threaded process, and they might just have one variable they share saying it's time to stop right now, perhaps an emergency stop type of indication. And in that case, we only have one shared object. Because the canonical pattern requires two shared objects, we can't possibly have out of thin air executions or read from untaken branch executions. So those are a few simple cases. Going ahead here, another one, this is a little more tricky. So we're going to spend a little bit more time on it. And this is unidirectional data flow. And the idea is that the data is flowing through the program from thread to thread in only one direction. Now, at first glance, it's like, great, this is safe, there's no cycles, but there are some tricks, and we'll go through them. Now, you have to be careful. The general approach is thread one is reading external states. We have this get external state function that has sensors 1 and 2 that it's reading. It puts them into some local variables S1 and S2. And it needs to take that state and do some kind of reduction on it, maybe convert it to standard units based on some calibration that's been done in the past. So we have reduced state 1 and reduced state 2 to do that. And we're going to talk about the properties that those two functions have to provide in a moment. Thread 2, meanwhile, asynchronously is picking up the most recent measurements. They might be measurements from two different loops, and that's okay. They're just measurements. They happen at some time. There's delay from the outside world through the sensor hardware in through drivers and whatever, and we finally get the stuff. So it's strangely ordered anyway, just due to the laws of physics. So a little more ordering is not a problem. But what we're going to do is we're going to take those two values you read, and we're going to compute a control action. And that's what the compute CTL function is. So all three of the functions, reduce state 1, reduce state 2, and compute CTL, all have to be coded carefully. You've got that little pure function thing, and we'll talk about that now. What that means, these have to be pure functions. They can't go around changing shared variables, obviously. But they also have to be pure and complete in the sense that no matter what bit pattern comes in through their arguments, they have to produce a definite value that cannot possibly introduce undefined behavior. All right, no divide by zeros, no stores off of the ends of arrays, nothing like that. It has to be written very carefully to avoid any trace of a possibility of undefined behavior. It has to be a pure function. And then once we computed this thing very carefully from the sensor inputs in thread 1 through the reduced state reduction and then across shared memory to thread 2, computing the control action, we use the set external control function to update the external state to provide whatever control is needed. Okay. There are some other examples of pipelines, but again, for the computations of these values, you have to be very careful because if you have undefined behavior, fun things can happen. Okay, at this point, I'm going to hand it back to Hans, who's going to talk more about what makes these idioms safe and unsafe.
Right. So, what makes something unsafe? Usually, what makes idioms unsafe, or what we already illustrated here, is that we load an atomic value with a relaxed load, and then we rely on that value for correctness. Either to determine the value stored into another atomic, so as in the simple example where we just copy one atomic variable to the other, or we rely on the value we get to avoid disastrous misbehavior. And Paul also just touched on that. Usually we get into the second situation by potentially allowing undefined behavior as a result of a misspeculated value. Next slide.
We do have a question. I'm sorry.
Okay. Yeah,
go ahead.
I saw that actually. Let's postpone that question to the end, I think, because we'll have a bunch of examples in the talk here, which I think largely answer that question. But yes, thank you. So this actually turns out to be surprisingly common, mostly due to relaxed loads that can lead to undefined behavior if they read a bad value. And generally, people don't think of them as potentially loading a bad value, and arguably in practice they can't. There's a lot of code that actually uses this pattern in practice and it works just fine. On the other hand, it's not correct in strict C++20. And as a result, it's very difficult to reason about, and we certainly don't know how to prove theorems about it. Next slide. So in general, the problematic idioms all have this pattern. We end up doing a relaxed load from an atomic variable, and then if we end up getting a bad value, we end up exhibiting bad behavior. And the problem is if we combine two of these together in two different threads, we again get this funny cross-reading behavior where we're reading the relaxed atomic value from something that was produced by the bad behavior in the other thread. And thus, again, if we somehow manage to misspeculate, the bad behavior can end up producing exactly the value that we read, and we can subsequently confirm the speculation, convincing ourselves that the result is potentially correct. Something which doesn't generally happen in real life, except in the sort of read from unexecuted branch kind of sense. But it's very difficult to preclude in the specification and very difficult to reason about. Next slide. So this is the first slide that kind of answers the question about what's this actually good for. So this is actually an idiom that's used in practice, but that we don't really know how to reason about. So what we're doing here is we're lazily initializing the atomic values X and Y. We're doing this by reading X, checking whether it has some special value that indicates it hasn't yet been initialized. Here I use 0. And then if it hasn't been initialized, we'll initialize it by just evaluating some pure function, which is guaranteed to always produce the same result. So it doesn't matter if I evaluate it more than once, and using that as the result, as the value of X, and assigning the result back to X. In general, for this sort of lazy initialization, we need stronger memory ordering, and we need to be more careful, but this is a really special case in which we're initializing a simple scalar value in an idempotent way, so that if multiple threads decide they have to initialize this, and they all do it, it actually works correctly, and the code has been written carefully to make that work. So in general, this should be correct, but the problem again is if we then trust the value of R1 and used it in a way so that if R1 is bad, we actually introduce undefined behavior, which I've indicated here by actually doing something concretely bad, which is assigning a random value to a random location, which is something that we believe undefined behavior can do. Then I again can get into the situation where if I have two threads, each performing one of these lazy initializations, and each potentially encountering undefined behavior, they're not even touching the same shared variable here, but they can implicitly touch the other shared variable by undefined behavior that stores to the lazily initialized variable in the other thread. So as a result of that, I can get the same bad pattern here. And again, this is the first of a couple of examples that are actually used in practice, but that we don't know how to reason about. And we would really like to be able to do that. Next slide. Okay, the next example is one that I believe is also used in practice quite a bit. And this is implementing a reentrant mutex, a mutex that you can acquire repeatedly in the same thread without deadlocking with yourself on top of an existing mutex. So the implementation strategy here is that we have a simple, a plain existing mutex, which we acquire at the outer level. And then if we acquire this mutex, try to acquire this mutex again, we'll carefully avoid locking this again and just keep track of how many times we've acquired the mutex. In order to do this, in addition to the mutex itself, we have to keep track of the owner of the mutex in an atomic, and we keep track of the count, the number of times the mutex is held. It's actually number of times minus one that the mutex is held. In the latter is held in a simple integer, which is protected by the mutex. The owner field is guarded in kind of a complicated way, in that it's we can modify it. We modify it only while holding the mutex, but we can read it without holding the mutex. And we guarantee that it's only the owner field is only changed to a particular thread ID and away from that thread ID by that thread. So no other thread can change the value to or away from my thread ID. Next slide. So the way the acquisition of such a lock works is basically, as I've indicated here. So if I try to acquire a lock, I first have to get my thread ID. I then check, is the owner me? Do I already own the lock? And that's safe to do without holding the lock, because no other thread can invalidate the truth of that test. Another thread is able to change the owner, but not to me or away from me. If I already own the lock, I just increment the count. Otherwise, I do something more complicated. I actually acquire the mutex, and then I store the owner field. Next slide. So this has the same sort of problem fundamentally, although this is more subtle in this case. The problem here is that if I test whether the owner is me, I'm doing a relaxed load, which I sort of abbreviated the relaxed load and the test into one statement here. I do a relaxed load of owner and check whether it's me. If somehow I end up misspeculating, so what I've indicated here in the particular execution, thread one, I'm in a case where thread one already holds the lock and does nothing special. If thread two sort of misspeculates that the owner field is actually me, what will happen is sort of both of them end up incrementing the count. I've indicated in the critical section here, as a result of this, I will end up with two threads in the critical section. I've made very explicit here that results in effectively undefined behavior in most cases. I've done this here by incrementing some variable x, which is protected by the mutex. And then if I see that more than one thread is in there, I do something bad. I store to a random location, sort of reflecting the potential undefined behavior here. So if I get two threads in this critical section, what can actually happen here is that the thread one will end up doing a random assignment to a random location, which can end up assigning to the owner field, which will end up satisfying the speculation in thread two, thus convincing thread two that its speculation was correct and it was okay to just go ahead and execute. So again, this is a more complicated example in which I have the same kinds of issue essentially. I have a relaxed load, I trust it, I act on that, and I get bad behavior as a result, which ends up satisfying speculation. So in strict C++20, without the out of thin air restriction, I again can get this bad execution. There's another question here. So why should I mess with such difficult code? It's very difficult to test. How can I test this code? And this is kind of our problem. This is indeed difficult to test. Well, a lot of concurrent code is difficult to test. You may want to avoid this kind of code. On the other hand, there are a number of cases where we actually rely on it inherently. I think the next slide actually has an example of where we pretty much have to rely on that today. And empirically, such code works, and it speeds up. It potentially speeds up programs significantly, since the use of memory order relaxed may avoid fences on the critical path, and this may be a huge performance increase. Whether or not you want to use this is up to you. Paul will talk more about examples where, in fact, it's memory order relaxed is perfectly safe to use. Next. So other important code examples that are not safe in strict C++20. The one that I've dealt with in the past is if we want to implement a concurrent garbage collector, for example, for Java. Very often it's the case that, it's typically the case that since the concurrent garbage collector needs to read pointer values that are being changed by the client code, I need to make sure that those concurrent accesses are safe. So the pointer values in the heap there essentially need to be treated as atomic accesses, and I need to make those relaxed because otherwise my Java code runs way too slowly, because I end up inserting basically ordering constraints or fences all over in the Java client code. So this is one example where I don't think there's actually a way out of this kind of code. Another interesting example is what's called chaotic relaxation, numerical algorithms that basically rely on just reading the most recent value in the most recent floating point value in a particular location without any sort of synchronization between them. Sometimes you can show from a numerical analysis perspective, that's fine. On the other hand, again, as a result of, with the absence of an out of thin air prohibition, we can get scenarios in which basically we end up getting an AND result somewhere more or less randomly through speculation, and then that ends up propagating everywhere. So there are at least theoretical scenarios here in which that doesn't work. Next slide.
Okay. No, one question we have, not used reentry mutex as examples in user space or kernel space. The case where you use this is in cases where you want to be able to have a piece of common code that does some operation requiring the lock, and you want to be able to call it whether or not you already hold that lock. And that's a pattern that happens fairly often, both in kernel and user space. It's not dominant. It's not a huge fraction, but it does happen. And we also have a repeat of why should I mess up with difficult code? How can I test that code? Concurrency isn't necessarily easy. The other point is, what we're saying here is that you need to use known good patterns. If you choose to just hack code together, concurrent code together, you're going to have problems, and even sequential consistency will not save you. Okay, so if you're doing concurrency, unless you're following known good, well-tested guidelines, yes, it will be very difficult. That's something that Hans and I have done successfully for a very long time, but I'll speak for myself. I know that I've messed it up occasionally and had to work hard to fix it. Why would we do this? Because in some cases, it gives you huge performance increases. There are cases in the Linux kernel where this kind of code has gotten multiple orders of magnitude speed up on some things. So, I mean, that's not something for that kind of speed up, I'm willing to invest some serious time and effort and some serious validation. In fact, my current employer, and I would guess Hans's employer as well, for certain sorts of things would be willing to pay a huge amount to get even 1% improvement, given the number of machines that both Hans's employer and my employers are rumored to have operating. So yeah, don't use it if you don't need it. You've got that point exactly right. If you can, keep it simple. If you can, just write single-threaded code. If that works for you, use single-threaded code, be happy. If you can use pure locking and not have to do any of this fancy stuff, do that, be happy. Get your job done, get on with life. But there are times when you have to go beyond that, and double-check locking is one example of this. So what we're doing here is, and this is a case where this is safe even in strict C++, and it's something that's used really heavily, and it's provably safe. So we've got this exonet, we load it, and we use a memory order require. We do a lock guard to do mutual exclusion, and then we repeat the load with a relaxed, okay? And then we do initialize it, and then we store the initialized value. So this is safe, and it's fairly easy to prove it's safe. We have an acquire, so the stuff that happens after that load can't reorder. Then we acquire a lock. Once we acquired that lock, the only stores to anything in X or related to X are with that lock held, so there can't be any racing accesses. And then once we release the lock, the other people will come in, see that exonet is already in thing, and they'll go by and do their business, and life will be fine. And that will avoid the possible confusion, undefined behavior that would occur if we let them run concurrently. This is the more complicated example, version of the example Hans gave earlier. All right, where he had a single value and therefore didn't have to be quite as careful. Okay, and why bother with this? Well, this lock guard mutex, that's a global lock. If in theory, ignoring performance and scalability, you could just acquire the lock and get the value out, and that would work just great theoretically. But you try that on a machine with 100 CPUs where you're doing it, and you'll find that you are getting much less throughput than you get out of a single CPU. So if you have a case where you have something that needs to be initialized once and is used really heavily by each of a number of CPUs, and by the way, 100 is an exaggeration. You could have problems with this on 16 CPUs. We've seen problems with this back in the day on 16 CPUs. And this small incremental amount of complexity allows very simple code to just work on very large systems, very scalably and very, very quickly. Let's take a look at and this is one where Hans mentioned I'd be talking ones where you didn't have any choice. This one, you have a choice in theory, but in practice on large machines, you don't have a choice. You won't get performance and scalability you need. The next example is one where even in theory, you don't have a choice, right? A common group of algorithms use compare and swap, compare and exchange in this case. And what's going to happen here is we're going to load a value from memory. and we can use a relaxed load. And the reason we can use a relaxed load is that we can, that the compare exchange is going to check for us. If we get a bad value, then it's going to say, oh, we don't have that. That does not match. And then we can go about our business. It'll fail. We'll try again. We have another question: is memory order release necessary for the stores in the mutex scope block? Let's go back and take a look here. In fact, there is a memory order store release if you look there. X init store is release, and the reason for that is so that it will pair with the acquire loads that are done later or at the same time. If they're done at the same time, they'll acquire the lock. That'll straighten things out. If somebody happens just at the time that init store completes, it'll be a release. They'll do acquire. Those will pair, and their later accesses will be guaranteed to see the initialization of X. Does that answer the question? Well, if not, we'll come back to it. So yes, you do need a release. You only need the one, and it only needs to be on X init, not on X. Okay, so back on the compare and swap. We have a load. We might have the speculation. You know, the compiler might be crazy and decide it wants to speculate and guess some weird value. If that happens, if that weird value is not one that ever appears, then the compare exchange weak is guaranteed to fail. We'll go and we'll reload, and hopefully it will be smart enough to get a real value this time. If it repeatedly speculates bogus values, I will file a bug against the compiler version to hopefully get it straightened out. So this is a case again where if you want to do certain concurrent algorithms, you have no choice but to use patterns that tolerate relax. You could use acquire if you wanted to for that load, but that would give you extra overhead on many systems, and in some cases that overhead is unacceptable. Okay, moving ahead. We're a little behind, so I'm not going to go into detail through this. I want to allow time for more questions. This is a table copied from an updated version of this working paper, which I'd hoped to have submitted yesterday, but life got in the way. And what we have is we have a bunch of categories. We've covered some examples in a number of these categories. Okay, and some of the categories are strict C++ safe. That's the last column. If it's got a capital Y there, that category, as far as we know, is safe and analyzable in strict C++ without the weasel wording, and life is good. If you can restrict yourself to that group, do so. Things will be easier, your life will be better. However, as we've seen, there are cases where reentrant mutex, we may need it to make it possible to make, you can, if you don't supply a reentrant mutex, your developers will invent one by hand and thus make all the mistakes that you can make. So put in your primitive, wrap it up, have somebody do it who can do it, test the bejesus out of it, and release it so people can use it. Hans talked about the lazy scalar initialization. We've also seen use of chaotic relaxation, and garbage collection is an important algorithm that is needed, and one where relaxed accesses are important for performance reasons. With that, summary. As some of the questions have hinted, I mean, you guys weren't just blowing smoke. Using memory order relax, it says right here, can be tricky because we don't yet know an efficient way to formally define the boundaries of out of thin air and read from untaken branch. There are important use cases that are necessary in some cases that work in practice, but we still don't have precise correctness arguments supporting them. What we're doing as a stopgap for part of this is we're defining a strict C++ 20, which allows us to precisely reason about some of them, some of the important ones, which is a good step forward. However, and there's many common relaxed usage patterns that are demonstrably correct in strict C++ 20. Even better news, I suppose, or additional good news, is that a lot of the other ones where we don't have a precise correctness argument seem to work in practice, and we have good reason looking at the implementations to argue outside of the scope of the standard, unfortunately, that they do in fact work. But we'd like to be able to bring that level of reasoning into the standard without, so we don't have to go inspect huge numbers of implementations. So with that, If you have more questions, and Hans made a list of references here for if people who want to dig deeper into this. Do we have more questions?
Actually, let me answer a question that wasn't asked but may have been implicit in some of the ones that were, which is, I think one of the motivations here is that there's potentially a huge cost difference between memory order relaxed and memory order sequentially consistent, or even the acquire release ones. So it's not uncommon on an architecture like ARM for that to be a couple of orders of 1 to 2 orders of magnitude, let's say, at least in the cache hit case.
Yeah, if you have, what Hans says is, I agree, and I've seen that as well. If you have a fast path and you've made things so that it works really fast, that extra memory barrier can, or that extra acquire load instruction can hurt you really badly. We got another question that has my name on it, it looks like. How is memory order consume doing? Well, not well, I guess is the shortest, honest answer. We do have some work going on. We had a session in the Linux Plumbers conference a couple of weeks ago where we looked at ways of making this fit in better. There's memory order consume is not the only use of dependencies by the Linux kernel that needs some help. Right now, we still use volatile accesses to make that work, and also some very heavy-duty coding restrictions. If you're using RCU dereference, which is what I'd like to be able to implement with memory order consume, but I can't because it just gets promoted to memory order require in all the implementations. That throws a memory barrier in there on some implementations, and that we can't live with on some architectures. So we still use volatile loads for that, and we still use coding restrictions. And I guess the next question is a follow-on there. There's a couple of different things that have been looked at, a couple different directions. One, some people at Apple, Jeff Bastian and Tim Northfield, if I got his name right, where they keep and this showed up as a working paper, which I unfortunately don't remember the number of at the moment, where what they do is they keep an extra quantity going with the pointer that tracks the dependency. And they carefully isolate that extra dependency from the compiler and then combine it with the pointer before each dereference, and thus prevent the dependency from being lost no matter what you do to the pointer in the meantime. That is a very cute trick. Some people object to the pointers growing in size. So another approach was done by a Google Summer of Prototyped, I should say, by a Google Summer of Code person myself, Akshat Garg. He was a student at IIT Mumbai, real bright guy. What he did was he took the volatile implementation of GCC and replicated it into a marking on the pointers that needed to preserve dependencies. And that got some discussion on the GCC list. Thus far, we haven't gotten a way of taking it forward farther, but hopefully we can get to a point where we can have a way of telling the compiler, this variable carries a dependency, please don't break it. And we also have an increasing number of places in the Linux kernel that depend on control dependencies, which are, at this point, we don't even have an agreed upon way of specifying how the control dependency works. So that's an even greater challenge.
Okay, there's one more question to which the answer is basically yes. So the question is, if I don't use memory order relaxed, do I have to worry about any of this? Or will I be safe from this sort of out of thin air issue? And so long as you also don't use memory order consume, which you probably don't, then the answer is yes. With memory order consume, things again get complicated. Well, except with current implementation, it's perfectly safe because it's useless, right? Because it turns into acquire. Sorry. This is true, yeah. With current implementations, it's true. It's fine, yeah. Another proviso I'll add to Hans's, which is he's normally giving to me, so I just turnabout's fair play. This is assuming that you avoid undefined behavior. If you don't use memory order relaxed, but you do use normal loads and stores, normal C language loads and stores on non-atomic variables that are shared, then sorry, all bets are off. So the other restriction you need in there is that all of your shared variables are atomics. The example with the while loop with compare exchange, say we're running on several cores. How does memory barriers, read-write barriers, I've seen this kernel compare in performance.
I'm going to read this again. The example with the while loop with compare exchange, say we're running on several cores, how does memory barriers, read-write barriers, I've seen this kernel code, compare in performance. So there's a couple things you might be asking. One of them you might be asking is, gee, if I'm taking the cache miss overhead I normally take with a compare exchange, am I going to even notice the memory barrier overhead? And that's going to depend on the hardware, but in many cases, yeah, if you're taking a cache miss on each and every operation, yeah, life will be hard. On the other hand, if you've been careful and you designed your algorithm to have good cache locality, so you're doing something where you have a quantity that's normally accessed by one thread but might be accessed at any time by other ones, just rarely is, then you will have a cache hit most of the time, and then that memory barrier is noticeable. And so in that case, you would want to use relaxed. Would you like to take the next question, Hans, about chaotic ordering?
I will try. I suspect neither of us is really an expert here. If I remember right, the original chaotic relaxation papers didn't talk specifically about memory ordering. Is relaxed absolutely needed for performance? I think any fire and forget plus equals could work. My understanding, based on talking to some colleagues who work closer to this area, is that basically you generally can't afford the memory, any additional memory barriers in a lot of this code. So in order to avoid the memory barriers, people tend to use memory order relaxed rather than something stronger. Or in fact, in many cases, they cheat and use non-atomic operations, which is strongly discouraged because it can just lead to incorrect results. So I don't have personal experience as to how bad this would get if you use stronger memory ordering there rather than memory order relaxed. But my impression from talking to people is it's not acceptable.
And to augment Hans's point about people using non-atomics for shared variables, I have to fight this battle all the time in a number of projects where you have people that just want to be able to say A equals 1 for a shared variable and believe it'll work, which it does a surprising fraction of the time. Anyway, we are past time. Hans and I do have some extra time. If you'd like to continue asking questions, including the one that just showed up, a couple just showed up, I'll copy and paste those. We're going to go to floor 9 of the Remo for this. Hans and I will be there. If you join us there, we can continue talking over the chat. And potentially we'll be able to talk to everybody, but I'm not going to count on that, given my ineptness with video conferencing, if nothing else. So again, floor 9 of the Remo, Hans and I will join there, and there'll be a general chat channel, and we'll answer questions on that, or any other way you can get them to us that we can see at the moment. And I'm going to copy and paste these last two, which might already be there, but who knows. In any case, for the rest of you, thank you very much for your time and attention, and good to chat about this with you.
Thank you very much.